In the 1960s, scientists from NASA Research Center were investigating methods of controlling liquids in space. Mainly due to the lack of gravity in outer space, they were looking for a method to control the fuel in the rockets. They developed ferrofluids, which are a colloidal suspension of magnetic nanoparticles such as Fe3O4 in a liquid. The nanoparticles typically have sizes of about 10 nanometers or less. These ferrofluids respond to an external magnetic field, which enable the fluid's location to be controlled through the application of this field. Ferrofluids can be prepared using metals like cobalt and iron, as well as magnetic compounds such as manganese, zinc, ferrite. Much research has been centered around ferrofluids, which contain small particles of magnetite Fe3O4. Magnetite can be produced by mixing Fe2 and Fe3 salts together in a basic solution. The particles must remain small and separated from one another in order to remain suspended in the liquid medium. Magnetic and van der Waals interactions need to be overcome in order to prevent the particles from agglomerating into larger particles. Thermal motion of magnetite particles smaller than 100 nanometers in size is sufficient to prevent agglomeration due to magnetic interactions. Surfactants prevent the nanoparticles from approaching each other too closely. A surfactant is added during the synthesis of ferrofluids in order to surround the small particles and overcome their attractive tendencies. For example, the surfactant is a long-chain hydrocarbon with a polar head that attaches itself to the surface of the magnetic particle. For my experiment, I'll be using vegetable oil to create a colloidal suspension. This structure creates electrostatic interparticle repulsion that can overcome the van der Waals forces, which would otherwise cause the particles to agglomerate. Ferrofluids have a wide range of applications. They've been used in rotating shaft seals where they behave as a liquid O-ring, reducing friction relative to that produced in a typical mechanical seal. These rotating shaft seals are found in rotating anode X-ray generators and in vacuum chambers used in semiconductors. Ferrofluids are also used in high-speed computer disk drives to eliminate harmful dust that could cause the data reading heads to crash into the disks. Another application of ferrofluids is in improving the performance of loudspeakers by bathing the electric coil in ferrofluid as a way to dissipate heat from excess energy supplied to the coil. This leads to better overall sound quality. Biologists have also been studying how ferrofluids aid in the migratory senses of animals. They've studied how trout respond to the magnetic fields of the earth, and it's thought that the trigeminal nerve enters the nose of the trout and may contain crystals of an unidentified mineral suspected to be magnetite, which helps signal when the migratory process should take place. Finally, ferrofluids may be used in future biomedical applications. Researchers are attempting to design ferrofluids that can carry medication to specific locations in the body through the use of applied magnetic fields. And in addition, ferrofluids are used as contrast agents for magnetic resonance imaging. Let's take a second to talk about magnets and how magnetism works. Common magnets are typically described as having a north and south pole. Similar poles, north-north or south-south, repel each other, while opposite poles attract each other, north-south or south-north. Unpaired electrons within a magnetic material are responsible for magnetic interactions. Electrons can provide contributions to magnetism by their spin angular momentum, meaning their rotation about their axis, and also their orbital angular momentum. Some materials are permanent magnets and through contact can cause magnetic behavior to other material. Here you can see I have my laser cartridge remnants, the powder. It's very messy and I shouldn't be doing this inside, but I have gloves on and figure I'm doing it on a glass table, so here's for the best. So I'm gonna take about 50 mLs of this powder and add a couple of tablespoons of my canola oil, approximately. I may have had a little bit more than the 50 mLs of the powder. I'm just taking something to stir it with And I'm really going to take my time stirring it because, oops, there's a piece of the printer cartridge that must have fallen out when I was emptying it out. And this is laser toner. Um, I was able to get a hold of one that was empty, and it was amazing how much of the magnetite was left inside of the cartridge that actually gets thrown away. And that's not even counting the stuff that gets thrown away in the little reservoir of the laser printer. I had a really big MRI magnet when I tried this yesterday. Before I had this powder, I actually went outside and took some iron ore out of the dirt, and I was able to have a little demonstration with that too. But since I was able to get the actual stuff today, I decided I would give it a try. But I couldn't find my MRI magnet, so I'm going to use the smaller rare earth magnet that I had access to. So I'm pouring the solution into a smaller cup so that it's thicker. And I'm going to hold it up so you can see. So I have to use my camera on my laptop because I can't seem to transfer the videos from my phone. So here I'm going to put the magnet up. Hold on, I'll hold it up a little bit more. I am not really seeing any spikes, but if you look real close, you could see that it does raise the ink up into like a little mound, and I'm able to spread it around like an Etch-a-Sketch. If you could see, it's definitely formed a magnetic fluid, and I am spreading it around on the outside of the cup. There could be different reasons why I'm not getting the spikes. It could be because my magnet is not strong enough. It could be because I have too much oil, too much solution separating those magnetic molecules. I'm even trying to hold the magnet over. I'm going to try this little stick that actually came out of the inkjet cartridge, which actually is magnetic. Just wanted to see, there's my dog, sorry. Just wanted to see if that works. But that didn't work either. So let me try one more thing. So here I've transferred my magnetic solution into a different container that has thinner walls, and I'm doing the same thing with my magnet. I'm running it up and down the sides, but basically what this experiment was, the purpose, what I was trying to do was to demonstrate the properties of ferrofluids to you, to show you magnetism, which is a force that acts as a distance between two materials due to properties of their electron spin and their orbital motions. Also, ferromagnetism, which is when the internal magnetic moments of multiple spin sets of unpaired electrons within the domain of the solid don't completely cancel, therefore they leave a net spin. That goes back to when we were discussing the magnets. Also, the ferromagnetism, phenomenon in which internal magnetic moments of unpaired electrons within a domain of the solid align and act cooperatively, forming the spikes, which are a pattern of uplifted particles that result from placing a magnet near the ferrofluid. They don't stick together. Why? Because a surfactant has been added. A surfactant is a molecular substance or salt that surrounds the particles, isolating them from the attractive forces of their neighbors. Why aren't they permanent? The individual particles of the magnetite behave as tiny magnetic domains. Therefore, in the absence of magnetic field and as a result of thermal agitation, the particles' magnetic domains become randomly oriented relative to one another. The magnetic domain regions where unpaired electrons strongly interact with one another and align even in the absence of magnetic field. I was hoping to show you some spikes, but like I said, there could be different reasons why my experiment didn't turn out. But I was glad to be able to at least use the proper ingredients for demonstration. Thank you.